Given two binary strings A and B, we need to return their sum as also a binary string. And a binary string is just a binary number represented as a string. So really, this question is testing whether you can do binary addition by hand and whether you actually understand the principles behind it. So first I'm going to do a quick refresher on binary numbers and addition. Binary numbers are expressed in base 2 and so only use the digits 1 and 0. In base 10, which is the number system that we're used to, each digit's place goes up by a power of 10. So for example, this number has a ones place, which is 10 to the 0th power, a tens place, which is 10 to the first power, a hundreds place, which is 10 to the second power, and so on. In base 2, each position goes up by a power of 2. So we start with a ones place, which is 2 to the 0th power, then there's a twos place, which is 2 to the first power, then a fours place, which is 2 to the second power, and so on. So adding numbers in base 2 is fundamentally the same as adding numbers in base 10, but we'll just be swapping the number 10 for the number 2 in certain places. So first let's break down how we might do this in base 10, and then we'll apply that to base 2. Let's try adding these two numbers first. 8 plus 5 is 13, but we can't just write 13 here because it's greater than 10, and we need to carry the 1. So how can we break down 13 into what goes into the ones place versus what gets carried to the tens place? The two operators that will be useful here are the modulo and the floor division operators. We can get the digit in the ones place by doing 13 mod 10, since that gives us the remainder after dividing by 10, which is 3. Then to figure out whether we have to carry or not, we can floor divide 13 by 10, since that'll tell us how many times 10 goes into 13 and then discards the remainder. The answer is 1, so we'll carry the 1 and then move on to the tens place. Since we have a carry this time, we need to add 1 plus 2 plus 4, which is 7, and then we'll do the same two steps again. 7 mod 10 is 7, so that becomes the digit in the tens place, and then 7 floor divided by 10 is 0, which means there is no carry. So the final answer is 73. We'll be doing the exact same steps for the binary addition problem, but use the number 2 instead of 10 for the modulo and floor division steps. So now let's look at the code. A will be this binary string, and B will be this one. When we do the addition, we need to start from the ones place, which is at the very end of the string. So let's create two pointers that will traverse the strings from the back. I will be the length of string A, which is 6, minus 1, so it starts at index 5. And we'll do the same thing for J, which starts at index 4. We'll need a variable to store the carried digit after we do the addition for each digit, which I'll call carry, and initialize it to 0. And finally, we'll create a list called reverse answer to hold the digits of our answer. Now the reason I'm using a list here is because I want to avoid string concatenation. We really want to avoid doing something like answer equals digit plus answer, and concatenate each digit to the previous answer string. Because strings are immutable, so the entire string has to be copied each time, which means each concatenation runs in O of n time, if n is the length of the answer string. And since we have to do this n times, the overall time complexity is O of n squared. So instead, we'll use a list to append each digit, where each append has an amortized time complexity of O of 1. This list is also going to store the digits in reverse order, because appending a digit adds it to the end of the list, but we need to traverse the strings from the back to the front, which means as we append digits, the digits that are in the higher places, which need to appear at the beginning of the list, will end up being appended at the end of the list instead. So the list will store the digits in reverse order, and then we'll reverse it again at the end. Now we're ready to start the main loop. This loop will decrement I and j at the end of each iteration, traversing the strings from the back to the front. So this condition means we'll continue looping until we reach the beginning of both strings. We also need to check if there's a carry digit left over at the very end, which you'll see an example of at the end. We'll start by casting the digits at each index to integers. Starting with string A, we'll cast a digit at index I to an integer if I hasn't gone out of bounds yet. Otherwise, it defaults to 0. Let's call this bit A, which is now the integer 1. And we'll do the same thing to the digit at index j and call it bit B, which is also the integer 1. Now let's add all three parts, bit A, bit B, and the carry, to get our total, 1 plus 1 plus 0, which is 2. From here, we'll figure out which portion of the total stays as the digit, and which portion needs to be carried over. To figure out the portion that becomes the digit, we'll do the exact same thing as we did in our example with base 10 numbers, but instead of doing mod 10, we're going to do total mod 2 since we're in base 2 now. 2 mod 2 is 0 because 2 divided by 2 is 1 with 0 as a remainder. So the digit in the ones place is 0, and we'll also cast that back to a string, since our final answer also needs to be a string. And let's append 0 to the reverse answer list. Then we need to figure out the portion that's carried, and again, we'll do the same thing as the base 10 example, but floor divide by 2 instead. 2 floor divided by 2 is 1, so we'll be carrying over this 1 to the next place. Finally, let's decrement I and j and move on to the next digit in the 2's place. Bit A will be 1 again, and so will bit B. We have a carry now, so the total is 1 plus 1 plus 1, which is 3. 3 mod 2 is 1, so the digit in the 2's place will be 1. And let's append that. Notice that this digit in the 2's place should actually be at the very left, but appending it puts it at the very right instead. And this is why this list is called reverse answer. Next, 3 floor divided by 2 is 1, so we'll have another carry of 1, and let's move on to the 4's place. Bit A is 0, and bit B is 1, so the total is 2. 2 mod 2 is 0, and we'll append that, and 2 floor divided by 2 is 1, so that's another carry of 1. And now we're moving up to the 8's place. Bit A is 0, and so is bit B, which makes the total 1. 1 mod 2 is 1, so we'll append 1, and 1 floor divided by 2 is 0, so now there's no carry. Now let's finish this up, and I'll show you what happens when there's a carry left over at the very end. Bit A is 1, and so is bit B, and there is no carry, so the total is 2. 2 mod 2 is 0, and 2 floor divided by 2 is 1. So let's carry over the 1 to the 32's place. Now j is out of bounds, but we still have a digit left for I, so we have to keep going. Bit A is 1, but since j is less than 0, bit B defaults to 0. 1 plus 0 plus 1 is 2, 2 mod 2 is 0, and 2 floor divided by 2 is 1, so that's our carry. Now when we decrement I and j, we see that both of them are out of bounds. But since the carry is not 0, this part of the condition is still true, and so we need to do one more iteration. I and j are both less than 0, so both bit A and bit B default to 0. The total is 0 plus 1, which is 1. 1 mod 2 is 1, so that's our final digit. And 1 floor divided by 2 is 0, so the carry is now back to 0. Now, after decrementing I and j again, we see that the carry is 0, which now finally makes this entire condition false. So we can break out of the loop and return the final answer. Since our list currently has all the digits in reverse, we can use the built-in reversed function, which will reverse a copy of the list to get the digits back in the correct order. And then we'll use the string join method with an empty string as a separator to join all the digits into a single string and return the binary string 1001010 as our final result. And we're done.